Before kind of really getting to the nuts and bolts of what an embedded system is, it's well worth revising over what we mean by a simple von Neumann architecture. So what I mean by that is, well, what does the CPU do? What does RAM do? What does ROM do? What does secondary storage devices do? And how do they all work together? Okay, so have a little bit of a recap over those ideas before moving into this lesson. That question on the screen, what are the main elements of a computer system, and write down as much as you can remember about basic hardware of a computer, is a good benchmark. If you can write quite a bit about the different parts of hardware and exactly what they do, then you're ready for this lesson. If not, stop now, go back, read over those main topics, CPU, RAM, storage devices, and then come back. So the basic layout of a PC is on the screen. So this is a very simplified diagram. So the CPU, remember, is at the heart. It's synchronizing the instructions. It's sending control signals to every single part of the computer. Okay, so CPU is connected to all the different devices using a bus. Okay, and that's information, those control signals that the CPU sends out, go down these buses. So it talks to RAM, stores temporary information RAM, the currently running programs, the currently in use data. The USB ports will allow us to connect mouse and keyboards and storage devices such as memory sticks and other things like that. And obviously you've got secondary storage in the form of maybe a hard drive. All these devices are located on the motherboard, so they will connect directly to the motherboards, and on the motherboard itself it'll have the buses which will take the information to the CPU. So the link on the screen will take you to a short video discussing the first modern computer. This is an interesting one to look through because it kind of gives a bit more indication of why we call the standard computer architecture the von Neumann architecture, and it's really kind of a little bit of a history lesson on it. So the reason why it's important to have a think about John von Neumann is that the von Neumann architecture was effectively named after him. So he's one of the key instrumental figures in actually setting up what we would know as a general purpose PC. So why is it named after him, the kind of standard architecture we use day in, day out? Well, very simply, before his invention, for want of a word, came about, programs were based on hardware. So what this means is that the programs were actually part of the hardware itself. So if I wanted to load a new program up, I'd actually have to take out hardware and replace it with new hardware. This was incredibly time consuming to do. So realistically, computers can only do one job at a time because it might take weeks to actually change programs. Okay, so that's very different to what we are used to. So we are very much used to being able to load up a program, swap programs whenever you want to at the drop of a hat. That just wasn't possible for the von Neumann architecture. So modern computers are all based on the von Neumann architecture. So this kind of diagram should be very familiar. So we have input devices like keyboards and mice and things like that. We have output devices such as monitors and printers. We have control units inside the CPU with an ALU. These are all the things that we have already been learning from day one, basically. So when the term von Neumann architecture comes up in an exam, it is really just asking you to talk about a normal computer. So don't get confused by it. I brought this up now because it's one of those things that just throws people sometimes. Okay, so don't let it throw you. Von Neumann architecture is essentially what we would know as a normal computer. So if you've not yet got notes on the von Neumann architecture, copy the image that was on slide 5, so you can easily Google this and type in von Neumann architecture. It pops up straight away. Make a note of what all those kind of parts are. This is kind of a revision over all the different parts of a computer. And if you want to, you can have a little extension and do research on the EDSAC computer and John von Neumann, just to kind of get some background history to how computers kind of are the way they are. So now that we've really kind of recapped the von Neumann architecture, it's time to kind of focus in on embedded devices. Now, when we say embedded device, what we really mean is a single purpose device which contains a microprocessor. So these kind of devices will only have one job and they will never do anything else. Some examples might be a washing machine. Now that might seem a bit of a weird. Why would a washing machine have a CPU? Well, it's programmable, isn't it? You can change the programs, you can set the temperature and all those kind of things. So we'll actually have some software running that behind the scenes. You might have an intensive care ward machine, so monitoring heart rates and other vital statistics. You might have a cockpit inside an airplane. There's a lot of software which is running behind the scenes to keep the airplane afloat and giving information to the pilots, but only has one job, and that job is to keep this plane flying. So these kind of devices, where they have a single purpose, but actually will also have software, are known as embedded devices. Okay, it's really important that you understand they are not general purpose computers. They're not going to have Windows installed on them. You won't be able to play Minesweeper while you're waiting for the washing to finish. But they will still be based on the von Neumann architecture. They will still have a CPU, they will still have some small amount of memory, and they will also have ROM. Now the software for these devices will normally be stored in ROM, okay, because we don't want it to be able to change it, we want it there forevermore. So let's look at an example of why a washing machine is considered of a Neumann architecture. Well, first of all, it will have inputs. Now, not all input devices are keyboard or mice. There are other ways of communicating with devices, and buttons and maybe little wheels you can turn are perfectly acceptable input devices. Output devices don't always have to be a monitor. It could be some water going into the washing machine, or the drum spinning, or the water heating up. Those are outputs of the system. The CPU is going to be running programs. That program is going to be controlling the water going in, when the drums should spin, when should spin fast or slow, and all those kind of things. So essentially taking the entire wash cycle and actually make sure it all runs as it should do. So in a similar vein, the airplane example will also have inputs. So this will take the form of sensors around the plane, and also controls inside the cockpits, the buttons and joysticks and all that kind of stuff. Output will be in the form of the engines, the instruments in the plane, so you can actually see what altitude you're at and things like that, and actuators controlling maybe wing flaps and things like that. The CPU will run the specialized software of the plane. Okay, so there is going to be a CPU behind the scenes running that software, and that software is required to keep the plane in the sky effectively. So embedded devices are very, very, very different. Okay, so the question becomes, well, why bother with this kind of specialized software? Why can't I just write a program like I would do in Python and run it through Windows or Mac OS or something like that? Well, they only have one job to do, which means they don't need all the additional complexities that you get with modern operating systems. So it won't need device drivers because it's got one set of devices which will never change. It does not need a GUI environment, so you're not going to have windows and icons, things like that. You don't need them. It has no need for memory management and multitasking because there are no other programs running. It's just that one single program. It won't necessarily need much security, so you won't be able to kind of hack into a washing machine and change the wash cycle. That makes no sense. And also file management. There's no need to save files. You won't be kind of making a Word document on your washing machine and then saving it. That makes no sense. So they have one job to do, and they don't need all the other kind of parts of an operating system which you would normally get. So they might need some of it, however. So for example, in an airplane, you would want some security, so you don't want anybody to be able to hack that because people might do that. But on a washing machine, not so important. So general purpose operating system will require lots of additional hardware, and there'll be no practical gain to it whatsoever. So why bother installing all this software and hardware when it's not needed? It will just drive the price up. So embedded systems tend to use very, very basic hardware. You're not going to have, an octa-core processor running on your washing machine because there's no need for it. It will be just powerful enough to run the software that it needs to run. As its special purpose, it can use 100% of all the resources of the system just for its own task. Okay, so you don't have to have memory management and things like that, because it just simply is just going to use what it needs. This makes it much more efficient than general purpose PCs, where you actually need a little bit more to be able to handle overhead, such as being able to swap processes, do multitasking, and all that kind of stuff. So now's the time to make some notes on this. So when you're making notes on this, do focus in what we mean by the term embedded system. Try and give 5 different examples. If you're stuck after 3 or 4, just Google it. There's plenty of examples on the internet. And just have a look around your house. You will find that there's lots of devices who have one job only. Look at those devices. Okay, avoid any device where there's apps. So for example, an Alexa or a smart TV, those would not be embedded systems because they have the ability to run multiple apps. Explain that they are still considered to be von Neumann architectures, because they will still have input and output, they will still have CPU, but specifically the software that they use is stored in ROM, which is very important, and one of the kind of main things the exam will focus in on. Now, as a challenge, and I want to make this very clear, you can have a look at the Harvard architecture, but this is A level only GCE. Okay, so you won't be asked in at GCSE what is a Harvard architecture, but in A level you will. Okay, so understanding the difference is important for A level, but not for GCSE.